Imagine this. In just 3 days, the sky and the Earth erupted in ways few thought possible. Two brand new stars suddenly flared into visibility, glowing bright enough for people to spot them without a telescope. At the same time, Venezuela was rocked by not one but two major earthquakes within hours of each other. And as if that wasn't enough, the sun hurled a massive wave of plasma, what scientists call a coronal mass ejection, right into the path of one of the rarest visitors in our skies, the interstellar comet 3I-IATS. This wild chain of events is now being called the 72-hour stack, because the odds of all this lining up are vanishingly small, less than 1 in 1,000. Normally, Earth might see one nova bright enough to catch with the naked eye in a year, sometimes none. But here, two exploded into view within just 36 hours. Venezuela, on average, only experiences a magnitude 6 earthquake every few years. Yet within one night the same region was struck twice, plus an aftershock. And then the sun's eruption happened to intersect with an object so rare we've only confirmed 3 interstellar comets in history. Statisticians say randomness can sometimes cluster events in ways that feel impossible, a phenomenon known as Poisson clustering. But this wasn't just rare, it was almost absurd. 2 novas in 3 days. That alone is a probability of point. Add in the earthquakes and the comet hit, and you're talking numbers that practically break the calculator. For astronomers and geophysicists, this wasn't just a busy week. It was a once-in-a-lifetime convergence that shook both the Earth and the sky. The first domino fell just after midnight on September 23rd. At 2:12 a.m. UTC, a nova called V1935 Centauri erupted, captured almost instantly by survey telescopes in Chile and South Africa. Alerts spread through scientific networks before sunrise in Europe. Then, less than 48 hours later, on September 24th at 10:21 p.m. UTC, Venezuela's seismographs lit up with a magnitude 6.2 quake near Men Grande. Locals felt the ground heave under their feet just as they were finishing dinner. But the Earth wasn't done. Only 6 hours later, another quake tore through the same region, as if the planet itself was echoing the chaos already unfolding in the skies. A second powerful quake strikes, this time magnitude 6.3, shaking the region from a depth of 14 kilometers. The ground hasn't even settled when aftershocks, some as strong as 5.8, roll through within the hour. Hospitals scramble to respond, their emergency logs filling up while WhatsApp messages fly, time-stamping the chaos in real time. But then, just 14 minutes after the second quake at 04:05 UTC, the sky adds its own drama. Astronomers everywhere get the alert. V7994 Sagittarius suddenly bursts into view, glowing at magnitude 6. Multi-wavelength sensors light up, detecting both gamma rays and X-rays, while automated discovery pipelines push the news worldwide. Professionals and amateur astronomers alike race to compare data, piecing together the unfolding spectacle. Meanwhile, something even larger is brewing. The sun is sending shock waves of its own. A coronal mass ejection, launched on September 25th, sweeps through the inner solar system. Models predict it could collide with the projected path of 3I-ATS, with timing narrowed down to an 8-hour window around midday UT. Every new solar wind reading triggers instant alerts from the Space Weather Prediction Center as scientists and comet hunters track the plasma front closing in. Across the globe, each event leaves its own footprint. Chile's telescopes capturing data in pre-dawn cold, Venezuela's hospitals fighting through a blackout, and solar physicists glued to live data streams. Together, these moments stack into a timeline of pure intensity, an extraordinary 72 hours of cosmic and earthly upheaval. And then comes the nova. This isn't just a star brightening, it's a stellar eruption. A white dwarf quietly siphons hydrogen from its companion until fusion ignites in a runaway explosion. The result? A blinding surge in light, up to 100,000 times brighter, briefly outshining a billion. That's what unfolded before dawn on September 23rd, when V1935 Centauri suddenly leapt to magnitude 5.8, just bright enough to be spotted with the naked eye from a dark field. In Valparaiso, Chile, amateur astronomer Gabriela Moya caught it first. Battling clouds and power outages, she stayed awake for nights, driven by determination. When her confirmed report reached the Central Bureau for Astronomical Telegrams at 0212 UTC, the news spread like wildfire across global networks. Soon telescopes worldwide locked onto the nova, and detectors picked up unmistakable gamma-ray and X-ray signatures as the blast ripped through space. What we were witnessing wasn't just light, it was the raw, violent heartbeat of a dying star unleashing its fury across the galaxy. That's the unmistakable fingerprint of powerful cosmic shocks, evidence that the explosion was hurling particles to near light speed and possibly even forging fresh dust grains in its wake. But the universe wasn't finished. Less than 2 days later, another white dwarf in Sagittarius, this one known as V799994 Sagittari, lit up the sky, climbing to magnitude 6.2, right at the edge of naked eye visibility. Its sudden appearance set off a scientific race. Survey teams rushed to claim the discovery, with telescope logs and social media buzzing as the reports rolled in. High-energy satellites like Fermi and Swift caught the event almost instantly, recording rapid bursts of gamma rays and hard X-rays. Inside NASA and among the Fermi team, debates swirled as experts double-checked the data, ensuring this wasn't a false alarm. When the confirmation finally went public, research papers exploded onto the scene, each one diving into the shock physics and particle acceleration behind the nova's violent outburst. What makes these nova stand out is their raw power. They aren't gentle flickers of starlight, they're thermonuclear runaways, stellar-scale detonations that send shockwaves through space. They happen in binary systems far beyond our solar system, yet their brilliance is so extreme that they etch their story across Earth's night sky for anyone lucky enough to be watching. But while the heavens blazed, the Earth itself was trembling. Just after sunset near Mene Grande, a magnitude 6.2 quake erupted at a shallow depth of only 7.8 kilometers, close enough to send the rupture racing straight to the surface. Homes shook, power lines swung wildly, and the local hospital, already stretched thin, rushed to set up emergency triage outside. Senior nurse Maricela Rivas, who had just clocked out, was pulled straight back in. Calm but commanding, she directed patients to color-coded tarps, spread across the parking lot, using her voice over the hospital's WhatsApp group to coordinate urgent care and supplies. Volunteers scrambled to rig water stations while the most critical cases were moved away from cracked walls. But the Earth wasn't finished. 5 hours later, a second, stronger quake struck. Magnitude 6.3, this time deeper at 14 kilometers, but almost directly beneath the same region. It followed a textbook pattern, one fault slipping, transferring stress to the next. Seismologists at the University of Los Angeles worked through the night, mapping the ruptures along the Oka Anon fault zone. Their models matched Omori's law: big shocks first, then a cascade of smaller tremors. Sure enough, within an hour, a 5.8 aftershock rattled the already shaken region, forcing patients and staff to evacuate all over again. With just 3 operating tables and power flickering on and off, Rivas and her team were forced into pure improvisation. Children in trauma cases were treated first, patients rotated outdoors when aftershocks struck, and flashlights were used to guide IV lines and monitor vitals. Local radio stations relayed updates, broadcasting supply needs and ambulance routes. For a time, the hospital became more than a medical center. It became the heartbeat of community survival and information flow. Meanwhile, geologists reminded the public, despite the terrifying timing, these quakes weren't random. They were the natural result of tectonic stress building, where the Caribbean plate grinds against South America. What looked like chaos was, in fact, the Earth following its deep, restless rhythm. When one fault segment slips, the stress shifts, sometimes igniting another rupture nearby. Each aftershock was a sobering reminder. In a week when the cosmos seemed to be rewriting probability itself, the Earth beneath still obeyed its own relentless rules. And above us, the sun was no less restless. Solar maximum isn't just a phrase this year, it's a daily reality. Sunspot counts have surged past 1065, and the solar radio flux is holding above 1. That's the kind of environment where coronal mass ejections become routine, with the sun hurling plasma storms into space every few days. But this time, something unusual is sharing the inner solar system with those storms. 3I Atlas. This isn't your ordinary comet, it's only the third confirmed interstellar visitor, and its orbit is far from typical. Strongly retrograde, nearly grazing the ecliptic, and screaming along at more than 60 kilometers per second, 3I Atlas isn't bound by our sun. It's a messenger from another star system. On October 3rd, it will swing within 0.19 astronomical units of Mars, close enough to put orbiters like MAVEN and TGO on high alert for imaging and spectroscopy. Most comets we study come from the Oort cloud or Kuiper belt, remnants of our own solar nursery. But this one, it carries the chemistry of a different sun, frozen into its ice long before our own star was born. And its timing couldn't be more extraordinary. Passing through just as solar cycle 25 peaks, it's plowing headfirst into the most energetic solar wind we've seen in over a decade. That makes 3I Atlas a natural plasma probe. Its coma and tail will light up as the solar wind crashes into it, revealing live how alien material responds to solar storms. Dr. Stefan Burns, a geophysicist studying Sun-Earth interactions, calls this a once-in-a-generation experiment. We've seen CMEs hit comets before, but never one from another star system. And with the Mars flyby, Planetary scientists are scrambling to capture every possible data point, hoping to decode both the comet's origins and the physics of solar plasma at its fiercest. But the show doesn't stop there. October is stacking up as a record-breaking skywatching month. On October 20th, 21st, comet Swan CIDOR 25R2 makes its closest pass to Earth, just at 0.26 astronomical units, about 39 million kilometers. The timing is perfect. A new moon ensures dark skies, and the Orionid meteor shower peaks on the very same nights. That means backyard observers will have a rare triple feature meteors, a comet's faint tail, and pristine skies. For the best view, head out after midnight, far from city lights. Let your eyes adjust for at least half an hour. A pair of 7x50 or 10x50 binoculars will give you the edge, and a simple sky chart or app will guide you to Swan's track, across the pre-dawn horizon. And then comes the date circled on every astronomer's calendar, October 20th. That's when 3I Atlas reaches perihelion, its closest approach to the Sun at 1.36 astronomical units. By then it will have endured weeks of buffeting by solar storms, offering scientists and skywatchers a front-row seat to an interstellar traveler's fiery encounter with our star. Even though 3I Atlas won't blaze across the daytime sky, some skilled observers may attempt twilight or dawn views. But safety comes first. Never look anywhere near the Sun without ISO 23122 certified solar filters, and never use binoculars or telescopes unless the filter is secured over the front lens. Just one unfiltered glance can cause permanent damage. For comet and nova hunting, patience is everything. Give your eyes time to adjust to the dark. Use a red flashlight or a dimmed phone screen, and you'll be amazed how much more detail you can pick out. The third major milestone comes on December 19th, when 3I Atlas makes its closest approach to Earth, about 1.8 astronomical units away. That's when the comet becomes most accessible for amateur imaging, especially if it grows more active after perihelion. Citizen science groups are already rallying. The AAVSO, the International Comet Quarterly, and the Comet Observation Database are calling for reports, magnitude estimates, sketches, time-lapse images. And if you do capture something unusual, maybe a sudden brightening, a kink in the tail, or even a tail disconnection, note the exact time, location, and equipment you used, and compare notes before submitting it. Responsible reporting filters out noise and turns individual backyard observations into real data for the global research community. If you're planning a group skywatch, especially with kids, build in a quick safety briefing before dusk. No direct solar view. Keep all optics pointed well away from the Sun. And if lasers are being used for pointing out stars, make sure they're handled carefully. The thrill of seeing something extraordinary is powerful, but a moment of caution protects both vision and credibility. As October and December unfold, the heavens are offering us a rare invitation, one we may not see again in our lifetime. And it comes on the heels of a breathtaking 72-hour stretch back in September, when two naked-eye nova, twin magnitude 6 earthquakes in Venezuela, and a coronal mass ejection colliding with 3I Atlas, all converged in what researchers now call the event stat. Statistically, the chance of that lineup was less than 1 in 1,000. Coincidence or connection? That's what the coming weeks will help reveal. With the Mars flyby, Comet Swan's approach, and Atlas's fiery perihelion, we're entering a season where nature itself is writing a story of extreme. And for once it's playing out right in